Hello there. This is a video on using substitution to evaluate integrals. Enjoy! This process is known as U substitution. Number 1, the integral of 3x squared sine of x cubed dx. This is a complicated looking integrand. 3x squared sine x cubed, that's called the integrand of this integral. And so we haven't done anything like this before. And so for this first one, what we're going to do is we're going to let u equal to x cubed. Well, if we let u equal to x cubed, then this becomes sine u. Sine u is something that we know how to find the antiderivative of. After we set our u substitution, we're going to differentiate u with respect to x. So we have du dx equal to 3x squared. Okay? Then we can rewrite this as 3x squared dx. Now, where have we seen 3x squared dx? We see it right here. 3x squared dx. So 3x squared dx is going to be replaced by du. And so what we have here is the integral of sine u, and then 3x squared dx is replaced by du. So we have rewrote the problem as the integral of sine u du. Well, the antiderivative of sine u is negative cosine u, and it's an indefinite integral, so we have to plus c. Finally, we want our final answer to be in terms of x, so we reverse substitute the u with x cubed, and so here is our answer. Okay, let's continue with number 2. Number 2, before that, let's look back at number 1. Why did we choose x cubed to be u? 2 reasons. 1, it would make this sine u, which would be much more simpler to do. And also, the derivative of our choice of u, x cubed, is 3x squared, which appears elsewhere in the problem. So those are the 2 guiding principles that we're going to do to decide what u should be. So let's look at number 2. Number 2, we have x times x squared plus 9 raised to the 5th. And so we think to ourselves, what would simplify this problem? Well, it would be much simpler if this was u to the 5th rather than x squared plus 9 to the 5th. If we take the derivative, du dx equals to 2x, and then we're going to move the dx on the other side, and then we're also going to multiply both sides by 2, or by 1/2, and so we have x dx. Look, this satisfies the other requirement, which is that x dx shows up elsewhere in our problem. So what we have here is the integral of u to the 5th, because x squared plus 9 is u, so we have u to the 5th, and then this yellow part, x dx, is equal to 1/2 du. So we're going to write 1/2 du in place of x dx. So then we have 1/2 times the integral of u to the 5th du. Well, the antiderivative of u to the 5th is 1/6 u to the 6th plus c. 1/2 times 1/6 is 1/12, and u is x squared plus 9. So we reverse substitute so that we have x squared plus 9 raised to the 6th power plus c. So this is our answer. Okay, let's look at the next example. Here we look at this, we examine this, and we look, okay, what would simplify this problem greatly? Well, this expression here, x cubed plus 3x squared plus 12, is being raised to the 6th power. So it would be nice if this whole thing was just replaced with u to the 6th. So that's what we're going to do. U equals to x cubed plus 3x squared plus 12. Then we're going to do du dx, and let's see what happens. 3x squared plus 6x. Well, we're going to move the dx on the other side. In that case, you got to keep this 3x squared plus 6x in parentheses. Now, if you look at this expression and this expression, they don't quite match. But if we factor out a 3, it would be quite nice, because we would have x squared plus 2x dx. We multiply both sides by 1/3, and we get x squared plus 2x times dx. And here it is, x squared plus 2x dx. X squared plus 2x dx can be replaced by 1/3 u. So this problem becomes 1/3 du all over u to the 6. Okay, this can be written as 1/3 the integral of u to the negative 6 du. All right, so now we're ready to anti-differentiate. The antiderivative of u to the negative 6 is 1 over negative 5 u to the negative 5 plus c. 1/3 times negative 1/5 is negative 1/15. And then u, we're going to back substitute. So x cubed plus 3x squared plus 12, that was what our u was. Raise that to the negative 5 power, and that's our answer. Okay, let's continue on. Number 4. Well, here, we can actually deal with this problem without that process of u substitution, but we're going to use u substitution to see how it works. So we look over here and we go, okay, 7 theta plus 5 is a little bit more complex than we would prefer it to be. It would be nice if it was just sine u. So we're going to make u equal to 7 theta plus 5. Then, just like before, we immediately take the derivative. This time is du d theta equals to 7. We're going to move the, we're going to move the d theta on the right side, and we're going to multiply both sides by 1/7. So we have this. This d theta is going to be replaced by 1/7 du. And sine of 7 theta plus 5 is going to be replaced by sine u. And so what we have here is the integral of sine u, and then d theta is replaced by 1/7 du. So then we have 1/7, and the antiderivative of sine u is negative cosine u. And then we have plus c. So then we have negative 1/7 cosine of, and u was 7 theta plus 5. So we reverse substitute, and we get this. Okay? Now, this problem could have been done by just putting a 1/7 on the outside in anticipation of reversing or undoing the chain rule. Let's look at number 5. Well, number 5, it would be nice if this denominator right over here was just one variable, like say u. So we're going to let u here be x minus 4. So then right away you take the derivative, du dx equals to 1. So du equals to dx. So this dx is going to be replaced by du because dx equals du. And then this denominator, x minus 4, will be replaced by just u. So here we have the integral of 3 over u, and then dx is replaced by du. That's nice. So the integral of 1 over u is natural log of the absolute value of u plus c. And so here we have 3 times natural log of x minus 4 plus c. All right, let's go on to the next page. All right, here's the next page. Here we have x minus 9 raised to the negative 2/3. It would be nice if it was just u to the negative 2/3. So we're going to let u equal to x minus 9. So du dx is equal to 1. So du is equal to dx. So this dx is going to be replaced by du because du equals dx. And so what we have now is the integral of u to the negative 2/3 du. The antiderivative of u to the negative 2/3 is 3u to the 1/3 plus c. So then we have 3 times x minus 9 to the 1/3 plus c. Okay. Next example. Here, it would be nice if the exponent here is just u. So here we have u equals to negative 9t, du dt equals to negative 9. Let me erase that right there. All right, so negative 9. So du equals to negative 9 dt, and then I'm going to multiply both sides by negative 1/9. So this is nice. This dt is going to now be replaced by negative 1/9 du. This exponent here, negative 9t, will be replaced by u. So we have the integral of e to the u, and then dt is replaced by negative 1/9 du. All right, so this is negative 1/9 the integral of e to the u du, and the antiderivative of e to the u is e to the u. And then we also have a plus c, and so now we replace u, we reverse substitute back with negative 9t. Okay. This is also a problem where u substitution is not really needed. You just, we did problems in the past where we just have to compensate or offset this negative 9 with a negative 1/9. But it's good to see this from u substitution point of view as well. All right, on to the next problem. Now this one gets a little bit more interesting. We have sine x times e to the cosine x. E to the cosine x is the problematic part of this integrand. But it would be very nice and simple if it was just e to the u. So we're thinking maybe u can be cosine x. Remember, there are two criteria to choose what's u. Criterion number one is what would make this be simpler looking. E to the u would be very simple. Criterion number two is if we take the derivative of what we made u, does the derivative show up elsewhere in the integrand? And yes, it does. Sine x shows up elsewhere in the integrand, which is what we want to happen. All right, so then we multiply both sides by negative 1. And so we have sine x dx. We have sine x dx right over here. So we're going to replace sine x dx with negative du. And we're going to replace e to the cosine x with e to the u. So what we have here is the integral of e to the u times negative 1 du. All right, so this is negative integral of e to the u du. Well, the integral of e to the u is e to the u. So you have negative e to the u plus c. Then we're going to reverse substitute cosine x back in for u, and this is our answer. Okay, let's go to the next one. This one is a little bit different. And if we were doing this lesson in class, I would have had each group kind of come up with different ideas and things like that. But for the purposes of this video, I will just show you how this is done. All right, so we're going to rewrite tangent theta as sine theta over cosine theta. Now what we want to do is we want to make a u substitution that will simplify this problem and whose derivative also appears in the integrand. So I'm going to go in reverse and already circle in yellow what I want to be able to replace when I take the derivative. And so I have to think, okay, the derivative of what is sine theta? And the answer is negative cosine theta. So in this case, I'm going to let u be cosine theta. So then du would equal to negative sine theta d theta. And I multiply both sides by negative 1, and I have negative 1 du times sine theta equals sine theta d theta. Oh, this is nice because what I circled in yellow is right over here. So I can replace what I circled in yellow with negative 1 du. And then I can replace this denominator with u. So then this problem becomes the integral of negative 1 du over u. Another way to write this is negative times the integral, negative 1 times the integral of 1 over u du. All right, the integral of 1 over u is ln of the absolute value of u. And then we also have the plus c. Then we reverse substitute the u the cosine theta back in for u, and so now we have this as the answer. Isn't that nice? It's a clever u substitution by rewriting tangent theta as sine theta over cosine theta, and by making u equal to cosine theta. If we made u equal to sine theta, this wouldn't have worked. You can try it, but it wouldn't have worked. All right, now we go on to yet another different kind of problem, and that's number 10. Now, number 10 presents us with a problem. If we just base it off of what I just said so far about u substitution and the strategy and the criteria we use, something falls apart here. Here's what I mean. Here we have x times the square root of 5x plus 1. This 5x plus 1 being square rooted, that seems to be the more complicated part than we would like. So it would be nice if it was square root of just u. So we're going to let u equal to 5x plus 1 so that this part right here could become just square root of u. As usual, once we make our u substitution, we immediately find the derivative. So du equals to 5. du dx equals to 5, so du equals to 5 dx. All right, so now I'm going to multiply both sides by 1/5, and so I have 1/5 du equals to dx. Now, we've got this dx right here, which is right here, so we're going to replace that dx with 1/5 du. So this is going to be replaced by 1/5 du. This part is going to be replaced by square root of u. But we have an issue. There's this extra x out here. What can we do with the extra x? Well, in this problem, we have a way of dealing with this extra x. I will take this u equal to 5x plus 1 formula, and I will solve for x. So we have x equals to u minus 1 all over 5. That is what we are going to replace x with, u minus 1 over 5. All right, so notice that we're going to replace everything with expressions that are in terms of u. All right, so let's bring it all together. I'm going to write it down here. So, like I said, the x is going to be replaced by u minus 1 over 5. The root 5x plus 1 is going to be replaced by root u. And the dx is going to be replaced by 1/5 du. Now, this looks kind of complicated, but it's actually really nice because I can distribute this root u into here and into here. At the same time, I'm going to combine this 5 with that 5 to make 1 over 25. So I have 1 over 25, and then u times root u, you see this root u and this u? U times root u is u to the 3/2. And then this minus 1 distributed to this root u is minus u to the 1/2. And then I still have my du out here. Now this is really nice because we can find the antiderivative. What is the antiderivative of u to the 3/2? It is 2/5 u to the 5/2. And the antiderivative of u to the 1/2 is 2/3 u to the 3/2. Close the parentheses and also put plus c at the end. Now we just reverse substitute. Replace u with what u equal to, which is 5x plus 1 raised to the 5/2 minus 2/3 and then 5x plus 1 to the 3/2, close the parentheses, plus c, and here is our answer. Now we can distribute this 1 over 25 if we wanted to, okay? But this is also an acceptable answer. All right, you might have to rewatch this example 10 to really get it. And so hopefully this was helpful. On to the next slide. All right, number 11 presents yet another interesting challenge. It says the antiderivative of 1 over square root of 16 minus x squared. Now recall, I'm going to write this on the side here, that the antiderivative of 1 over the square root of 1 minus x squared dx is inverse sine of x plus c. But this has to be a 1 right there. but there's a 16 right there. So how do we make this work so that I can use this even though this over here says 16? Well, here's how. First, I'm going to factor out a 16 from within the square root. So this gives me 16 times parentheses 1 minus x squared over 16. Okay, and I still have my dx out here. Okay, then I'm going to take out the root 16 and make it just 4. And then I'm going to make the square root of 1 minus. Now I'm going to be writing x squared over 16 as parentheses x over 4 all squared. Now what we have to do is we're going to let u equal to x over 4. Why? Because then this part can be just 1 minus u squared, which would match the same format as over here. And so I'm going to let u be x over 4. Immediately, I'm going to take the derivative. So du equals to 1/4 dx. And then I'm going to multiply both sides by 4. So 4 du equals to dx. All right, so you see this dx that I'm circling in yellow? It's going to be replaced by 4 du. And then over here, what I'm circling in green will be replaced by u, because x over 4 equals u. All right, so let's put this together. Okay, I have dx is going to be, or 1 over 4 square root of 1 minus u squared. And then remember, this dx is replaced by 4 du. So 4 du, that's dx. Maybe I'll circle it in yellow as well. And then here I'll circle that in green. Okay, all right. Pause this video if you need to look at this a little bit further before moving on. All right, now what's nice is that the 4's cancel. Okay, so this becomes the integral of 1 over the square root of 1 minus u squared du. This looks exactly like this over here, except it's in terms of u. So then this is inverse sine of u plus c. And then I will reverse substitute and replace u back with x over 4 plus c. And so there's your answer. Okay, let's see how this works with an inverse tangent antiderivative. Number 12. Okay, in number 12, recall this one. The antiderivative of 1 over 1 plus x squared dx is inverse tangent of x plus c. Okay, but this over here says 1 plus x squared, but this one says 9 plus x squared. So how do we force this 9 to become a 1? Using a very similar strategy as what we did in the previous problem. We're going to factor out a 9 from x squared plus 9. So that becomes 1 plus x squared over 9. Okay? And just like before, I'm going to rewrite x squared over 9 with x over 3 squared. So now we're going to let u equal to x over 3 so that this will just be 1 plus u squared. Okay? All right, so du equals to 1/3 dx. Multiply both sides by 3. 3 du equals to dx. So this dx that I'm circling in yellow will now be replaced by 3 du. And the green that I circled will now be replaced with u. Okay? All right, so let's see how this goes. 1 over 9 times 1 plus u squared. And then dx is replaced, remember, by 3 du. Maybe I'll circle this in yellow as well. Okay? All right. Now, the 1/9 I can just take on the outside. And so I have 1 over, and there's a 3 too. So let me erase this 1 over here and put a 3 over here. Okay? All right. And then this is 1 plus u squared down here. All right, this is nice because the 3/9 becomes 1/3, and the integral of 1 over 1 plus u squared is the inverse tan of u plus c. So now I will reverse substitute and replace u with x over 3. And so here is my answer. Okay? All right, number 13. Now, if you would like to try number 13 on your own, first, pause the video and then unpause it when you have tried it on your own. Okay, let me give you a moment to pause if you would like. All right, now let's look at it. The integral of cosine squared x sine x dx. Remember what we said earlier, we want to choose a u that will simplify this problem and whose derivative will show up elsewhere in the integrand. I have a sine x dx here. So that's probably what I'm going to try to tailor this to. So then I got to make u cosine x so that when I take the derivative, I will have sine x dx show up. And so I'm going to multiply both sides by -1, and I have sine x dx. Perfect, because that is what I circled, so that's replaced with that. So this is actually a pretty simple one. Cosine squared x is replaced by u squared, and sine x dx right here is replaced by -1 times du. And so I have negative integral of u squared du. The antiderivative of u squared is 1/3 u to the 3rd plus c. Reverse substitute. Cosine was u was cosine, so cosine cubed x plus c. All right, on to the next slide. Okay, now we're going to find definite integrals instead of indefinite integrals. Notice that there are numbers here now. This one says the integral from 0 to 2 of x squared times the square root of x cubed plus 1 dx. So how do we handle it when we have numbers here and we have to evaluate this definite integral? Well, we start off similar to what we did. We have to find a choice for u. Well, u equals x cubed plus 1 would be a good choice, because then this would just be square root of u. Furthermore, the derivative, being 3x squared dx, has this x squared dx part in it. Look at this x squared dx. That's over here. So I'm going to multiply both sides by 1/3, and I have my x squared dx. This is fantastic, because I'm going to replace x squared dx with 1/3 du. All right, so this becomes the integral of the square root of u, and then x squared dx is replaced by 1/3 du. Now, these two numbers, 0 and 2, those are x values, because this is an integral in terms of x. So this lower limit of integration is x equals 0, and this upper limit of integration is x equals 2. But now we have switched over to u values. So we have to find the corresponding u value to an x value of 0. So what you do is you just plug 0 in for x in your u substitution, and you plug 2 in for x in your u substitution, and you have 1 and 9. So 0, the lower limit of 0 becomes 1, and the upper limit of 2 becomes 9. So this is 1 and 9. So it is very important for you to remember that we must replace the upper and lower limits of integration with u values, with corresponding u values. All right, so now we have 1/3 the integral from 1 to 9 of u to the 1/2 du. All right, the antiderivative of u to the 1/2 is 2/3 u to the 3/2. Just like before, you can draw a vertical line and put a 1 and a 9 here. So we're going to plug in, first of all, this part, I'm just going to rewrite that as 2/9. Okay, let me write it now. 2/9 u to the 3/2, 1 to 9. All right, so what we're going to do is we're going to plug 9 in for u and plug 1 in for u and subtract. All right, so 9 to the 3/2 is 27. 1 to the 3 halves is 1. So then I have 26 times 2 over 9. So that's 52 over 9. And that's my answer. Remember, the answer to a definite integral is a number. Okay, I'm going to actually talk about an alternate way of doing this problem as well. An alternate way of doing this problem is to leave the limits of integration blank for the time being. So notice that right here, I'm writing this exact same line over here, but without any numbers here. Okay, so then I'm going to treat this like a indefinite integral. So I have 1/3 times the integral of u to the 1/2 du. And the antiderivative of u to the 1/2, again, is 2/3 u to the 3/2. And normally it's plus c, but now I'm going to replace things back. So I have 2/9, and instead of u, I'm going to replace u back with x cubed plus 1. If you do that, then you can use the original limits of integration, because now I'm dealing with x again. So it's kind of up to you. I prefer you doing the blue method. It's a little bit more clearer and more mathematically correct as far as notations go. With this, it's not as great. I need a plus c here too. And so if you do it the green way, I would prefer you not to put an equal sign right over here. I would just have you take out that equal sign and start anew. All right, so then you have this. So you have 2/9. I'm going to plug 2 in, so 2 cubed plus 1. And then I'm going to plug 0 in, 0 cubed plus 1. And so I have 2/9 times, this is 9 minus 1. Oh, did I make a mistake somewhere? I feel like I made a mistake somewhere. I know my mistake. I forgot the 3/2 that is supposed to go over here. Silly me, silly goose. So I need a 3/2 right there. So this one has a 3/2. This one has a 3/2. The 9 has a 3/2. The 1 has a 3/2. Now we are good. All right, 9 to the 3/2 is 27. 1 to the 3/2 is 1. And we get the same thing, 52 over 9. Okay? All right, let's see how this works out in number 15. Just like before, if you would like to try number 15 on your own before I do it on this video, pause the video and give it a try. All right, so here I'm going to make u equal to tangent theta. Why? Because then this part would become u cubed, and the derivative of tangent theta appears elsewhere in the problem. So it really makes perfect sense to make u tangent theta, because the derivative of tangent theta is secant square theta. So here, this secant square theta appears right there, and it's going to be replaced by u. And so what I have is the integral of u cubed times du. It was that simple. All right, but we got to change these numbers, 0 and pi over 4. So u of 0 is tangent 0, which is 0, so it's still 0. U of pi over 4 is tangent of pi over 4, which is 1. So this pi over 4 is replaced by 1. All right, now look how simple this problem suddenly became. All right, so we have the integral of u cubed is 1/4 u to the 4th, evaluated from 0 to 1. And we can just use 0 to 1 because 0 and 1 are u values. We converted it to 0 to 1, and we have u's. So 0 and 1 appropriate. So we have 1/4, and then we have 1 to the 4th minus 0 to the 4th. So your final answer here is 1/4. Okay? All right. Try number 16 on your own first by pausing the video. All right. Let's finish out this video. And I know it's been a long video. I apologize with this final question right here. All right, now, some of you may still be thinking, how do I know what u to choose? Well, it takes practice and it takes experience. Here, what I'm going to say is, look at this x dx. That is what I probably want to have happen when I take the derivative of whatever I'm making u. And so nicely, and it's nice that we have this down here. Now, if that denominator was just u, then we might have a natural log type of integral going on. So let's see. In fact, that is what I'm going to make u. U equal to x squared minus 4. I take the derivative, which gives me 2x dx. Perfect. There's my x dx right here. This is my x dx right here. Let me move the 2 over. So you have 1/2 du equals to x dx. So this part is going to be replaced by 1/2 du. All right, so now we have this problem right here. The integral of 1 over u times 1/2 du. This 1/2 du is the yellow part, and this u was the green part, because we made u equal to x squared minus 4. But we got to change these two numbers, 0 and 1. So u of 0 is equal to 0 squared minus 4, which is negative 4. So the 0 becomes a negative 4 down here. And then u of 1 is 1 squared minus 4, which is negative 3. So this upper number is now negative 3. All right, so once again, make sure you are changing these limits of integration into their corresponding u values. All right, so I have 1/2 times the integral of negative 4 to negative 3 of 1 over u du. All right, the antiderivative of 1 over u is the natural log of the absolute value of u, evaluated from negative 4 to negative 3. All right, so now I'm going to put negative 3 in for u, and then negative 4 in for u, and subtract. So I have 1/2 times natural log 3 minus natural log 4. Now that already is the right answer, but if we want to write it in a simpler way, we apply the property of logarithms, and this becomes natural log of 3/4. All right, now on the next slide over here is a list of antiderivatives that you already know, that you should already know. So as part of homework, I want you guys to fill in every single antiderivative over here, okay? Now, not the bottom of the page though. The only one that you know from the bottom of the page is this one, because it was one of the examples that we did. But we'll develop the rest of these later on, okay? But for now, fill out the top half of this last page. All right, that's all, folks. Bye-bye.